Class, welcome back. We have another video on section 4.4. Today we are focusing on end behavior. Things that I want you guys to keep in mind. So far, our videos, and again this one, we are finding and really working with puzzle pieces right now. We need to focus on these materials that we've been doing the last couple of videos, because tomorrow, or the next time I see you, or the next video, you're going to be putting all of this stuff together and creating graphs of functions. Alright, so the last little bit before we start graphing is to talk about end behavior. An end behavior is an equation that tells us how the graph will act at its ends. Okay? It's an equation that tells us how the graph will act at its ends. Now, two of these three kinds of end behavior we already know. And if we review a little bit from our last videos, we know that if the degree of the numerator is equal to the degree of the denominator, okay? So if the powers or the degrees are the same, top and bottom, well, then we use y equals, and we say LC top over LC bottom. What do I mean by LC? Who can help me? LC equals leading coefficient. Alright, so we have that already. We remember that one. The other one that we know is when the degree of the denominator is greater than the degree of the numerator. And that one's super easy. We just say, whenever that occurs, the horizontal asymptote will always be y equals 0. Okay? So in these two situations, degree of denominator is bigger, you use y equals ratio of the leading coefficients. If the degree Oh my gosh, I goofed up. If the degree of the denominator is the same, if the degree of the denominator is the same as the numerator, then you use the ratio. If the degree of the denominator is greater, then you use y equals 0. And now we introduce our next little piece here. Okay, so an oblique asymptote. An oblique asymptote might look something like this, right? We talked a little bit about that. We've seen those now in pictures. This is just a slant asymptote, or a slanted line. It's still linear. Okay, it's linear, but it's slanted. The other thing I want you to know is we could have some crazy stuff. We could have a graph have something like a parabola. Alright, that is another option. So we can have parabolas or cubics. I'm just going to use etc. because you can also have like quartics or other things like that as well. Okay, and these two types of asymptotes, okay, these occur when the degree of the numerator is greater than the degree of the denominator. Okay, if the degree of the numerator is greater than the degree of the denominator, then we do long division. Alright, we do long division. We are looking for the quotient, okay? I'm going to put another little star. We only need the quotient, and we ignore the remainder then. Alright, that's why I wanted to add that little line. We only need the quotient, so we ignore the remainder. The last thing just to kind of keep in mind, this long division, it can be done on the original or the simplified function. Alright, and hopefully you'll see what I mean in a little bit. So, today, really, a lot of what we're going to be doing is focusing on these two types on the right side and really practicing figuring out how to work with these types of things. Sorry. Alright, so let's jump into our first example. I might not do all of these just for your sake. We'll address that as the time comes. But okay, this is already telling us in this first example that we have an oblique asymptote. So we know we are going to have a situation where the numerator's degree is greater. So when we check, Yep, x to the fourth, that's a higher degree than x cubed. That is exactly what we thought would happen in order to have an oblique asymptote. So the trick here is we need to long divide. So we write our dividend, 3x to the fourth. Remember to put all of those placeholders in. I don't have an x cubed, so I'm putting 0x cubed minus x squared plus 0x plus 0. Alright, I want to put all those placeholders in just so I can see what's going on throughout the entire problem. And I'm dividing this dividend by my divisor, x cubed minus x squared plus 1. Alright, now we know the tricks here. We know what we're supposed to do. We just did this. We need to figure out what is this x cubed missing to make it look like 3x to the fourth. And hopefully we agree the answer is 3x. Alright. If I multiply 3x, if I distribute this to all three pieces, all three terms of my divisor, I would get 3x to the fourth. What do we have here? Negative 3x cubed and I missed this, plus 3x. I almost wrote that in the wrong spot. Now please remember what we do. We change our signs, or we subtract, right? So I'm going to subtract, which means I will add, and then of course this will now be a subtract. We get a cancel, we get a 3x cubed, we bring down our x squared, we have negative 3x. And then we can keep bringing down to 0. All right? We rinse and we repeat. We ask, what is this x cubed missing to make it look like 3x cubed? The answer is a positive 3. When I distribute the positive 3, I get 3x cubed. I get negative 3x squared. I get positive 3. I draw my division, or sorry, my bar, and I say cancel. Oh shoot, my bad, I forgot to change my signs. So I subtract, I add, and I subtract. Now they cancel. Now I get 2x squared minus 3x minus 3. Now what you need to understand here, guys, we can't go any further, and the reason is because the degree here is larger than the degree of my new dividend. Alright, so we are done, and if you remember correctly from the first page, we do not care about the remainder. Okay, so to answer this question, we would say there is an oblique asymptote, and it is at y equals 3x plus 3. That was my quotient. That is my oblique asymptote. Alright? Okay, let's check out another one. When I take a look at this next example, okay, we're looking at a lot more now. We need to first start by checking out the domain. Alright, and let's see here. It looks like I can... No, I can't factor the numerator, but this bottom, this denominator, that's a difference of cubes. Okay, a difference of cubes means that I can factor it. So I'm going to say 2x to the fifth minus x cubed plus 2. And then if you guys remember, what we're looking for is if you have an a cubed and a b cubed. Alright? It's always going to be a, b, a squared, AB, B squared. Now, I on purpose did not put any symbols in. And the reason I did not put any symbols in is because it all depends on what the original was. If this is a plus sign, then this will be a plus because it's same, and then this would be a minus because it's opposite, and then this would be a plus because it's always positive. What if this had been a minus, though? This would be a minus, so this would be a minus, and then this would change to a plus. Alright? So what I need you to remember here is if you can see a cubed and b cubed, it always factors in this pattern. AB, a squared, AB, B squared, and then you just have to figure out the signs. So I look at my original, x cubed minus 1, I know that that's going to be x and 1, which means this is my a and this is my b, so this is going to be x squared, and 1 times x is x, and 1 squared is 1. So the only thing I have to do now is take into consideration the sign. My original was a minus, so it's minus, or the same, and then it's the opposite, and then it's always positive. Now the reason that we do this is because we need to see if there are any pieces in the bottom that we can find a restriction for. And hopefully you remember, well, this is a restriction. We get a restriction from this x minus 1. So when I write my domain, I'm going to say all real numbers, but I also know that x cannot equal 1. All right, and that comes from right here. When you use the sum or difference of cubes, this will never be factorable, so you will not be able to get a solution from this to include in the domain. There will not be any restrictions from that. All right? So we remember from last video, hopefully, that any restriction in the domain has to be seen as either a whole or a vertical asymptote. And if you guys remember, wholes only occur when you cancel. All right, vertical asymptotes occur with what's left. All right, is there anything that cancels? No. So I do not have any wholes, and I need to say that by putting a line through it. Vertical asymptote, I have this x cannot equal 1. That means that there's what at 1? Yep, there's a vertical asymptote at x equals 1. All right, now, end behavior. Before we move on, I need you to understand end behavior. The ends can only act one way. All right, you can't say they act horizontal, like a horizontal line, but then also a slant asymptote or a slanted line. All right, so what you need to understand is only one will occur. All right, only one of these will occur. And to figure out what it is, well, we need to kind of look back at the original here. My degree of the numerator is greater than the degree of the denominator, which means I'm going to have either an oblique or an other. So we need to do some long division. So let's do it. 2x to the 5th plus 0x to the 4th minus x cubed plus 0x squared plus 0x plus 2. Put that in the box. And then we are dividing by x cubed minus 1. All right. When I do this, hopefully we agree, I'm thinking I'm missing 2x squared, right? X cubed, to turn that into 2x to the 5th, you'd have to multiply by 2x squared. And when I distribute, that leaves me with my 2x to the 5th, and then minus 2x squared. All right? Draw our line. Don't make a mistake like me. Make sure you switch all your signs. So cancel. Nothing's happening here, so I'm just going to go right to negative x cubed plus 2x squared plus 0x plus 2. Oh, and we're almost done. We are almost done. I know that I need to figure out how do I turn x cubed into negative x cubed, or what's it missing? It's just missing a negative 1. So this becomes negative x cubed. This becomes positive 1 when I change my signs. Cancel, and I'm left with 2x squared plus 1. All right? Okay, now here's the deal. You have to remember, we can't go any further, so this right here is the remainder, and you know what? I don't care about it right now. Okay? It's not going to help me with anything. What I care about is my quotient. It's 2x squared minus 1, and we need to decide, is that a horizontal, an oblique, or another? Well, it's not horizontal. We should have known that originally, right? We knew from our recognition of degrees it wasn't going to be horizontal. I hope that you can make this connection. This is not oblique. It's not oblique because it is x squared, which means it is a quadratic or a parabola. So you need to understand that you will have to put this under other. 2x squared minus 1. And then the last thing, please, please, please remember, let me know that you understand that there are not horizontal asymptotes or oblique asymptotes. All right, let's try to get through at least 2 more in the video, and we will see how we do after that, okay? So, this next example, I like this one because you can factor it a little bit more than the first one. So let's take a look. Ooh, I think I can factor both top and bottom here, so yeah, let's do that. I know, oh, come on, black pen. There we go. Okay, x and x, ooh, same thing on the bottom. X and x. So how do we get factors of -10 to +3? +5 minus 2. Yes, perfect. Okay, so that's good. Let's see here. How do we get to +8 from factors of +15? I'm thinking 3 and 5, right? 3 times 5? Yeah. Okay, this is good. This is good because we can now very nicely see what we're going to put for our domain. We know for our domain we're going to have to put all reals except x cannot equal -3 and -5. So those two values are restricted because they are in the denominator. Now what's really nice is we can continue and we can say, ooh, I see an x plus 5 here and here, so we cancel it out, and now we know that we really have x minus 2 over x plus 3. That's what our function is going to look like. The last thing we really need to do is kind of examine what's going on with those different restrictions, and then also what type of end behavior this is going to have. So please remember, if something cancels out, that leads to a hole. That leads to a hole. So I know I'm going to have a hole at -5 because -5 canceled. Sorry, x plus 5's canceled. My vertical asymptotes occur with whatever is left over. So this x plus 3 is going to lead to a vertical asymptote at -3. And this should make sense again. Why? Because anything that was a restriction in my domain has to either be a hole or a vertical asymptote. Now, to get the y value of the hole, it's honestly as easy as just plugging in. Alright? So -5 minus 2, -5 plus 3 is -7 over -2, or I would just say 7/2. Alright? Okay, last thing, end behavior. End behavior. Take a look. You can look at the original. You can look at what you got now. And either way you look at it, I hope you notice the degrees are the same top and bottom, right? Squared, squared, or first, first. This is good. That means that they have equal degree, which means we do what to find the asymptote? It's going to be a horizontal asymptote, and it's going to be at the ratio of the leading coefficients. So y equals, well, leading coefficient of 1, leading coefficient of 1, 1 over 1 equals 1. Alright, so if we really wanted to say it in just one nice little line, we would say y equals 1. Alright, I just wanted to show a little bit of my work. Alright, awesome. Let's get through one more, and then we will call it a video. I know I'm already talking long enough. Alright, let's do this top one. Let's do this top one. I like this one, especially just because it requires us to do a little bit of fraction work before we get started, right? We have two fractions separated, or I guess technically we only have one fraction, but I can make that into a fraction. And we know that if we want to add fractions, we need to have common denominators, so I need to go by x and by x. Alright, that's an x. So this will become 2x cubed plus 9 all over my denominator of x. Easy enough, right? Not that bad. But again, this is something that I want you guys to recognize. You need to be able to recognize what's going on here and understand how you're going to have to combine these. All right? Okay, so we take a look at our original function now. This is, I would say, is our original function. It's the same exact thing as this, just written in a different way. And I say all reals except x cannot equal 0. How did I get it? I had an x in my denominator. So when I set that not equal to 0, I get that. Now, does this cancel out? No, it does not. Okay? This does not cancel out. So this is not a hole. This is just a vertical asymptote at x equals 0. The last thing you need to keep in mind is end behavior. In end behavior, you have to figure out what's going on with the degrees of the top and the bottom. So we look. Numerator is a degree 3, denominator degree 1. That means what? The top is larger than the bottom, and we have to long divide. Got a long divide. So we go through it. It's the same procedure. It's the same type of algorithm every single time. To get from x to 2x cubed, I need 2x squared. And when I multiply, I get 2x cubed. And I change my signs. They cancel. I just get a bunch of zeros. All I have is 9. I cannot put x into 9, right? I can't figure out how to do that. So this is my remainder. And what do we say? I just don't care about it right now. I just don't. All right? What I care about is my quotient, 2x squared. That is a quadratic, which means it has to go in which column or which section? Is it a horizontal, an oblique, or another? It's another. So y equals 2x squared. Last thing, just remember, put some lines through there, and we should be good to go. All right, I think I'm going to stop the video here. I think we will definitely do 1 or 2 more in class the next time I see you. But again, this is what I would like you to have done for now. Let's just quickly take a look again what you should be able to do at this point in time. And again, this is all leading up to graphing in a day or two, is we want to know if you can determine the end behavior and what type of line it's going to be or what type of equation it's going to be based on those rules about the degrees. Okay, so you have to look at degrees for that. And then really the only other thing is can you perform the long division to help you come up with those equations. Alright, so that is it for today. I hope you have a great day, and I will see you next time.